Hello, everybody. Today we're going to talk about reference angles, okay? This is the beginning of a new chapter for trigonometry. This is the beginning of chapter 3. In chapter 1, we talked about the basics of trig, and it was mostly on a coordinate plane. You know, we talked about that the input was always an angle and the output was always a ratio of two lengths of a right triangle, or two sides of a right triangle. And so we had, kind of defined trigonometry that way. We got into chapter 2 and it was all about right triangle trigonometry. And we were talking about SOHCAHTOA, and all of a sudden we were dealing with opposite, adjacent, and hypotenuse. And now we're in chapter 3. We're going to go back a little bit to coordinate plane, but we got to get this idea of reference angles. And so without any further ado, let's talk about reference angles. A reference angle is the acute angle. Now this is important. A reference angle is the acute angle. It's the acute angle between the terminal side of an angle and the x-axis. Now that can sound pretty wordy, but I want to make sure we understand what this is. A reference angle is the acute angle in between the terminal side of an angle and the x-axis. So for instance, if I drew an angle in standard position, it was right here. So of course, this is the initial side, and we're saying, boom, this is the terminal side in the third quadrant. And what if I told you that that angle was 230 degrees? The question is, what is the reference angle in that case? Well, the reference angle is the acute angle in between the terminal side, okay, so this is the terminal side, and the x-axis, and this is the x-axis. So I'm looking for the acute angle in between those two things. I'm looking for this angle right here, okay? And so the question is, how big is that? Now, hopefully everybody listening and watching this can answer that question. You know it's 90 degrees to get to here. It's another 90 to get to here, so that's 180. So the fact that we're at 230 means we're a little bit past 180. So you could take 230, subtract the 180, and what you'd have left is 50. And that's what that angle is, 50 degrees. So the reference angle of a 230 degree angle is 50 degrees. Now, sometimes it's a little bit different. Sometimes we're looking at them and maybe the angle is, I don't know, right here. And we'll call this angle right here, we'll say that this is 110 degrees. Now, 110 degree angle, again, let's look for the reference angle. Well, it's going to be the acute angle in between the terminal side and the x-axis. And so this time, again, that angle is going to be here, but it's not going to be so easy before. Before we did whatever we were given, minus 180, and then we had the reference angle. Well, we can't take 180 from 110. So we got to think about this. I don't want you to know a formula. I want you to understand the big picture. I know that it's 180 degrees if I went all the way to here, but I didn't go all the way there. I stopped right here. So then the question is, how big is this other part? Well, it's however much I would need to add on to get to 180. So I can take 180, subtract the 110, and I'd be left with 70. And that's what that angle is. So the reference angle of 110 degrees is 70 degrees. All right, and those are reference angles. Every quadrant works a little bit different. Here's 4 examples. Okay, in quadrant 1, when we talk about the reference angle being the angle in between, the acute angle in between the terminal side and the x-axis, well, every angle in quadrant 1 is its own reference angle. The reference angle of 70 degrees is 70 degrees because it's the acute angle in between the terminal side and the x-axis. When we get into the second quadrant, that reference angle is over here. And so the reference angle is going to be whatever it would take to get all the way to 180. In this case, 20 degrees. In the third quadrant, the reference angle is right here. And this is always going to be how much bigger it is than 180. So 250 minus 180 will give me 70 degrees. And lastly, for the fourth quadrant, we haven't seen any like this. For the fourth quadrant, the reference angle is right here. And so it's how much it's less than going all the way around. So you could take 360 and subtract what you have. And so in this case, the reference angle, 360 minus 300, would be 60 degrees. And that would be how much I'd need to make it all the way around. Okay. Now there's formulas that you could use for each one of these. Obviously for, like I said, for the quadrant 1, it's always just whatever the angle is. Okay. For quadrant 2, it's always going to be 180 minus theta. Okay. For quadrant 3, it's always going to be theta minus 180. And for quadrant 4, it's always going to be 360 minus theta. But see, I don't want you to memorize formulas. And this one's for quadrant 1, and this one's for quadrant 2, and so on. I don't need that. I want you to be able to take a big picture look at this and use a little common sense, realizing if I know where that angle is, what would the reference angle have to be? How big would this piece have to be? And I think you can figure that out for each one of these. So I'd like you to try for this next set. You can go ahead and look at these 4 right here. And I want you to find the reference angle for each one of these angles. It shouldn't take you long, but you can still go ahead and pause the video, and then I'll go through the answers in just a second. Okay, let's talk about this. The reference angles, okay? So for first quadrant, we said the reference angle always is the angle that it is if it's in the first quadrant. So the reference angle is 60 degrees. In the second quadrant, it's going to be this part right here, which is whatever it takes to get to 180. So the reference angle is going to be 30 degrees. For this one, it's going to be right here, so it's always going to be how much past 180 it is. So the reference angle is 80 degrees. And for this one, it's going to be how much do I have to go to close that off. And so how much more do I have to go to get all the way to 360? Well, that would be 50. So the reference angle is 50 degrees. Notice the reference angle is always acute because it has to be. The reference angle is always the acute angle in between the terminal side and the x-axis. Now, I'm not sure if you have thought about this yet, but there should be one big question on your mind. And that question is, why? Why do we care what a reference angle is? What's the point of a reference angle? Here we're doing all this work talking about theta minus this or 180 minus theta. Why? Why would we care about what a reference angle is? And I can't explain that in a quick answer, but I can show you in a problem. And so that's what I'm going to do. What I'd like you to do is I'd like you to try to draw something like this, if you can, okay? And what I've done is I've labeled this. Notice I've got 4 angles drawn, all on the same coordinate plane. And I'm going to say that this angle right here is theta 1. I'm going to say this one over here is theta 2. This one down here is theta 3, and this one down here is theta 4. Now, what I'm saying is I'm trying to say that those are individual angles, kind of like this. So theta 1 is this one, theta 2 is that one, theta 3 is that one, and theta 4 is that one. And those are all these angles right here. Okay, I'm just, to make it easier, I put them all on one coordinate plane. So I'm saying that the one thing they have in common, everyone should be able to see, and what is it? What do they all have in common? Well, each one of those angles, theta 1, theta 2, theta 3, and theta 4, all have a reference angle of 30 degrees. Okay, so that's a start. They all have a reference angle of 30 degrees. So now I want you to figure out, what does each one of those thetas have to be? Well, theta 1 is the easiest, because theta 1 is whatever the angle is, 30 degrees. Theta 2, if the reference angle is 30 degrees, you got to go, well, how far is it from here to here? Well, that would be 150. Theta 3, that would be all the way from here to here, so that's going to be 30 degrees past the 180. It's going to be 210. And theta 4, well, it's going to be from here all the way to here. That's going to be 30 degrees shy of 360, so I got to take that back, and it's going to be 330. Okay, so if someone questions you, what in the world are you doing right now, or what in the world are you learning right now? You could give them a very articulate, intelligent-sounding answer by saying, well, I've just learned that 30 degrees, 150, 210, and 330 all have the same reference angle, which is 30 degrees. And like I said, that sounds really good. But again, we haven't answered the question, why? Why in the world do this? Now I'm going to show you. What I want you to do is I want you to imagine, can you find a point that's on the terminal side of that angle, that 30 degrees? And if you feel like you can't, you're wrong, okay? You can easily find a point there. And so what I want you to do is I want you to think about our special right triangles for a second. Imagine a 30, 60, 90, okay? And what if I told you, now in a 30, 60, 90, we typically called the small side x. We said the hypotenuse was always double whatever that is, so it's 2x. And the longer leg was x times the square root of 3. But what if I gave you how long one of the sides was? You should be able to determine all the other sides. So if I know this is 30 degrees, and I told you that this was 1, well, then the short side would have to be half of that. And then this longer leg would have to be 1/2 times the square root of 3. And another way of saying that would be square root of 3 over 2. Those are the same thing. Okay? Now, what we can do is look at what happens if we put a coordinate plane on top of this. Now I can find that point right there because I know how far out on the x-axis I went to get there, square root of 3 over 2. And I know how far up in the y direction I went to get there, 1/2. And so now all of a sudden I have the coordinates of a point on this angle, square root of 3 over 2, 1/2. And why is that helpful? Well, that's helpful because if this is the x and the y, then I could figure out some of the other information, something to do with trig, for instance. Remember, this right here is the hypotenuse, so that's also the r. So in that whole idea of x squared plus y squared equals r squared, this is the r. And so I know that sine theta is y over r. So what's sine theta in this case? Well, sine of 30 degrees would have to be y, which is 1/2, over r, which is 1. Well, anything over 1 is just that thing. And so then I know that the sine of 30 degrees is 1/2. Okay, now that's pretty neat. But what I want you to see is imagine in this picture, there exists a point over here that's like a reflection of this quadrant 1. And again, notice what's going on here. We would have a special right triangle. So in the same case, if this part was 1, then how far back we moved in the negative x direction would be negative square root of 3 over 2. How far up we moved in the y direction would be positive 1/2. So it'd be negative square root of 3 over 2, positive 1/2. And again, the radius would still be 1. If we thought about a point back here, again, we could reflect this down, and now we would again have a special right triangle. And if this was 1, then this would be 1/2, and this would be square root of 3 over 2. So you can think about, we went negative square root of 3 over 2 in the x direction, and we went negative 1/2 in the y direction. And then that same point would kind of exist over here. And this one, we know, again, we can make a special right triangle, and this side right here is square root of 3 over 2, and this side right here is 1/2. So the coordinates of that point are square root of 3 over 2 and negative 1/2. So that means that I could find not only the sine of 30 degrees, but I could find the sine of 150. Because the sine of 150 is going to be just like the sine of 30 degrees, but maybe the sign, the positive or negativeness of it changed. So what's the sine of 150? Well, it's going to be y over r. The y value is right here, 1/2. What about the sine of 210? The sine of 210 is going to be y over r, which is going to be negative 1/2 over 1, which is negative 1/2. And lastly, the sine of 330, not 333, but 330, is going to be y over r, which is going to be negative 1/2 over 1, or negative 1/2. So now let's answer the question, why? Why is any of this important about reference angles? Here's why. Because if you know the reference angle, then you can realize that you can find the trig values of a bunch of angles, all if you know one. Knowing what the values or what the point is on 30 degrees gives me all the information I need about 150, about 210, and about 330. I can use this to figure all these other things out. So I'd like you to give this a try. Hopefully you've caught along enough to follow, but I want you to try this one right here. This one, I've changed it, so now the reference angle is 60 degrees. Again, I still have theta 1, theta 2, theta 3, theta 4. And I want you to find the sine of each one of those. So you can pause the video right here and give it a shot. I know you can do it. And see if you can try it on your own, and then I'll do this one for you. Okay, let's give this a try. First of all, we got to figure out the angles. Theta 1, that's easy. That's 60 degrees. Theta 2, well, it's 60 degrees short of 180, so that's going to be 120. Theta 3 is 60 degrees beyond 180, so that's 240. And theta 4 is 60 degrees shy of 360, so that's 300. Okay? Now, Now we got to figure out the sign of all these. But let's go back to the special right triangles. And let's think about if I had one that was stood up like this, and it was a 60, 30, 90. Okay? Now, if I said that this is 1, right here, the hypotenuse, then this side would be 1/2, and this side would be square root of 3 over 2. And again, I can lay that down on the coordinate plane, and now all of a sudden, I know what a point is. I know that point I had to go over 1/2 in the x direction, and I had to go up square root of 3 over 2 in the y direction. So this point right here would have to be 1/2 square root of 3 over 2. And then if I kind of reflected that point back over here, then that point would have to be, well, it went negative 1/2, went negative in the x direction, but again, square root of 3 over 2. And then a point down here would have to be negative 1/2, and then negative square root of 3 over 2. And lastly, a point right here could be positive 1/2, but then negative square root of 3 over 2. And from this, I can figure out the sine of all of these angles. The sine of 60 degrees is equal to y over r, which is going to be square root of 3 over 2 over 1, so therefore square root of 3 over 2. The sine of 120, again, is going to be y over r. So it's going to be square root of 3 over 2. The sine of 240 is going to be y over r. Now this time y is negative, so it's going to be negative square root of 3 over 2. And lastly, the sine of 300. And the sine of 300 is going to be y over r. And so that's going to be, again, negative square root of 3 over 2. So why are reference angles important? Because if you can learn some of the information about some of the angles in this first quadrant, then when you realize that all of that information applies to the second quadrant and the third quadrant and the fourth quadrant, then you can use your knowledge of reference angles to find out information about every angle anywhere. And this is a big deal. So what I want you to do right now is let's think about, what if I was going to try to apply this to just a totally random problem? It says the secant of 315. And you're going, okay, what's the secant of 315? Well, first I'd have to back up and go, well, secant theta is always what? Well, secant was the inverse of cosine, so it is r over x. That's what secant theta is. And then I have to ask myself, well, where in the world is 315? Well, 315, you go 90 to get to here, 180 to get to here, 270 to get to here. Well, it would be about here. And what that, you go, okay, so that's 315 degrees. So what is the reference angle in here? Well, how far short of 360 is that? And if I take 360 and subtract 315, I get 45 degrees. So the reference angle is 45 degrees. Again, I can think about this in terms of special right triangles. You can think of a 45, 45, 90. And go, if the hypotenuse was 1, then the shorter sides would be 1 divided by the square root of 2. Now, you could rationalize the denominator and make that square root of 2 over 2. I'm completely good with that. How I did that is I multiplied the top and bottom by square root of 2, and you get square root of 2 over 2. But I'm okay with either answer, this one or this one. Oddly enough, our book uses both. It just kind of picks and chooses here and there. So, what does that mean? Well, that means that I could pick a point, that this point right here, if this was a coordinate plane, that point right there would have to be square root of 2 over 2, square root of 2 over 2. Those are the x and y coordinates of it. And so this point, there exists a point on this one, of this 315. That would be positive square root of 2 over 2, because it went in the positive x direction, this way. But then it went in the negative y direction. So it'd have to be negative square root of 2 over 2. And so that's what the x and y values are. Now, also, though, I know that the r value is 1. And so then if I'm thinking about secant theta, I can say, well, I now can figure this out. The secant of 315 degrees is equal to r, which is 1, over x, which is square root of 2 over 2. And when you divide by fractions, you flip and multiply. So that would be the same thing as 2 over the square root of 2. Okay, the secant of 315 is 2 divided by the square root of 2. Again, we should think about rationalizing the denominator. And if we do that, we get 2 times the square root of 2 over 2. These cancel out, and we just get square root of 2. So in final, the answer, the secant of 315 is square root of 2. Now, all of a sudden, having some knowledge about the special right triangles and reference angles, I can figure out all sorts of trig functions from all over the place. So now using that, I want you to try these three real quick. Pause right here, and then we'll work through them in just a minute. Okay, let's take a look. So I'm going to move through these quickly because I'm guessing that you did them already, so you don't need me to move too slowly. First of all, we're going to talk about 60 degrees. Oh, we're not. I'm doing this wrong already. I'm getting ahead of myself. First thing I need to do is I need to draw this and go, okay, 150 is going to be right here. Okay, and so then what is the reference angle inside here going to be? And the reference angle, if this is 150, it's how much short of 180 is it? So that reference angle has to be 30 degrees. So we think about our 30-degree special triangle, 30, 60, 90. And we know that this right here went in the square root of 3 over 2 x direction, and it went up 1/2 in the y direction. And so that point would be square root of 3 over 2, 1/2. Okay? Now, and we know that the radius is 1. So the cosine of 150, well, you think about that point over here. The only thing different is this time the x is negative. So it'd be negative square root of 3 over 2, 1/2. And if cosine is x over r, then we can take negative square root of 3 over 2 over 1. So therefore, the cosine of 150 is, maybe not that big, negative square root of 3 over 2. There you go. All right, let's look at the next one. One kind of got away from me. Got a lot of stuff here. Okay. So we know that one's out. All right, let's look at the next one. Tangent of 240. What's the first thing we should do? Well, we should draw it. 240 degrees is somewhere around here. Why? Well, because I know it's 180 to get to here, and I know it's 270. I know it's 270 to get to here, and it's not quite to 270. So we go, what again is the reference angle? Well, it's how far past 180 it is. So 240 minus 180, this is 60 degrees. So you think about things in terms of a 60-degree angle, or 30, 60, 90. If this is 1, this part is 1/2, this part is square root of 3 over 2. Think about that in terms of the x and y axis, and this point right here would be 1/2 square root of 3 over 2. But in tangent 3, both x and y would be negative. Now we know that tangent theta is always y over x, and in this case that would be negative square root of 3 over 2 divided by negative 1/2. Now, a couple cool things happen. The 2's cancel out, and the negatives cancel out. And you're left with square root of 3 over 1, which is just square root of 3. So the tangent of 240 degrees is square root of 3. Awesome. Last one, cosecant of 315. Well, again, first thing we should do is draw it. And 315, like we saw a minute ago, is over here, okay? The reference angle is 45 degrees. And so I got to think about a 45, 45, 90, okay? And if the hypotenuse is 1, then in a 45, 45, 90, this side is 1 divided by square root of 2, okay? And this side is also 1 divided by square root of 2. Then we put that on a coordinate plane. We realize that this point right here, that's pretty easy. 1 divided by square root of 2, 1 divided by square root of 2. All right, so there's my x, y, and my r. I know that cosecant is what? What is cosecant? Well, cosecant is the inverse of sine. So cosecant theta is r over y. So therefore the cosecant of, not of theta, but of 315 is equal to r, which is 1, over y, which is 1 divided by square root of 2. Well, when you have fractions and fractions, you flip and then multiply. So you'd flip that 1 and it would just be square root of 2, because it's square root of 2 over 1. All right, hopefully these are the answers you got, and hopefully I've made some sense of why reference angles are so important and what they are. Have a great day.